Maximum of random characteristic polynomials.
Okay, first I'd like to thank the organizers for giving me opportunity to speak about this activity, this nice workshop, and I'd like to thank Asaf for providing his notebook for this presentation, because I had an accident with my laptop on Tuesday with aggressive liquid orange juice stained really the screen, so it cannot be used for presentation, for nice presentation any longer. Okay, so I'd like to, this presentation will be based on mainly on recent work with Nick Sim, which is in the archive, but I also necessarily will mention previous works, relevant works with John Keating and Grace Harvey. So what is all this story about? So take ensemble of random matrices. I will deal mainly today with two classical ensembles. One is ensemble of Gaussian Hermitian random matrices known as GUE, Gaussian Unitary Ensemble, where random matrices are sampled with probability density proportional to exponential of minus 2n trace of h squared, and this normalization ensures that asymptotically all eigenvalues are supported in the interval from -1 to 1. And let us consider the corresponding characteristic polynomial whose polynomial whose zeros are eigenvalues of the corresponding matrix. But let us look to this polynomial basically as a random function and try to just plot it. Here I just plotted for a singular realization polynomial normalized in the appropriate way. We will see why this way of normalization is convenient, and we see that for example, size of the matrices is not that big, and 50 still they show reasonable variations. But when we increase the size to 3000, then I already, in order to plot it in a way that we can appreciate fluctuations, I need to use log. Otherwise, or I can use, of course, logarithmic scale. So we see that this is this polynomial, when one varies spectral parameter across the range containing many eigenvalues, shows huge sorry. Shows huge fluctuations, and goal of my talk will be to characterize some properties of this fluctuating random function, and in particular I'd like to discuss the probability distribution of the global maximum of polynomial when we take many realizations of the ensemble of random matrices. So what do we know, or we believe to know, about this random variable, a maximum of characteristic polynomial? This is the prediction, and you will see that it's quite detailed prediction. So consider the maximum of recentered. Recentered means that we just subtract mean value of the log of mod of characteristic polynomial, and we are interested in the value of the maximum for this log mod, from which we of course can, by exponentiating, extract the value of modulus of polynomial itself. So the prediction is that this random variable asymptotically for large n behaves in the following way. There are two leading terms, 2 log n and -3/2 log n, which are non-random, they are deterministic. And then the next term of order of unity is random, And this random variable y can be characterized explicitly by exponential moments, or which is the same two-sided Laplace transform, which is given in terms of Euler gamma functions, and this capital G stands for the Barnes d gamma function. So, and normalization can be also explicitly calculated in terms of so-called Glacier-Kinkelin constant related to derivative of Riemann zeta function. So this is the result, and the goal of this talk eventually to show you how one arrives to this type of result. Let us compare this prediction with numerics. So what is done? Since this is prediction, so y can be obtained, or we'd like to compare really to sample numerically this random variable, and then we plot y. So this maximum, we subtract these two terms, and then compare with the prediction. It turns out that in order to get good agreement for not that big sizes n, one needs to introduce also a shift, some shift, but and then one gets a really nice agreement with predicted probability density, which is this broken line is obtained by numerically inverting or recovering the probability density from this formula. And here we just plotted a histogram for n 3000 and that many realizations of the ensemble. And in order to satisfy ourselves that this is our prediction is sensible, we check how this shift changes with growing size of the matrix, and we see with a good will that really this shift decreases. Decreases completely clear. Or our prediction that asymptotically it tends to 0, but this is of course left to goodwill of those who look at this graph. But we believe that this numerics supports our prediction. Now, second ensemble, which is a second standard ensemble in random matrix theory, is so-called circular unitary ensemble introduced by Dyson many years ago. Basically, we take n by n unitary matrix chosen random according to higher measure uniformly from the unitary group, and then, since all eigenvalues of such matrices have modulus 1, the complex variables with modulus 1, so they are on the unit circle in the complex plane. So reasonable definition for the characteristic polynomial is then this, with spectral parameter being exponential, just denoted as exponential minus I theta. So we speak then about these angles theta in the interval 0 to pi. And again, we are interested in statistics of the modulus of characteristic polynomial defined in this way over the full circle 0 to 2 pi, in particular in its maximum. And prediction is, again, first two terms are precisely like in the previous case, the same 2 log n minus 3/2 log n, then variable of order of unity, but this variable for this here is the difference with the previous case. Now we even can explicitly write down the probability density without using the Laplace transform. It's given in terms of so-called Macdonald functions, so it has a very explicit form, and it shares some similarities and of course differences. It's not exactly the same as for the case of Gaussian unitary ensemble, but it shares some properties. In particular, what should be noted that in both these cases, the distribution of this variable y, so of extreme value or maximum, is differs from the so-called Gumbel distribution, or maybe more correct name will be Gumbel distribution, because this is a German name by a very interesting person. You may enjoy reading about his life in Wikipedia, for example. He was among the first 30 people deprived of German citizenship personally by Adolf Hitler. So really very brave person. And this is a distribution, Gumbel distribution, bears his name, is a distribution of maxima of collection of either uncorrelated random variables with all finite moments, or in fact it can be extended to much broader class of short-range correlated variables, and in fact it's quite robust. But here we see interesting example of non-Gumbel statistics, and I will argue that really there is accumulating evidence in recent years that this is a new universality class of so-called logarithmically correlated variables. In particular, at present only some insights exist for logarithmically correlated Gaussian variables, so I will discuss mainly Gaussian case. But there are reasons to believe that it goes beyond that. So anyway, one can show that this distribution and also distribution. Wait. I'm not sure that waiting will help. Okay, basically this distribution and that distribution, which is characterized in terms of its double Laplace transform for GUE case, they share the same left tail, which behaves as modulus of y, or y tending to minus infinity, modulus of y exponential of y. In case of Gumbel, there will be no this modulus of y term. So this is main difference from Gumbel in the tail, but there are also some other features. And also this 3/2 is a typical characteristic value, this constant 3/2 of this new universality class for uncorrelated variables. Leading term is the same, okay, provided we normalize variance to 1. But here, instead, there will be just 1/2. And this transmutation of 1/2 to 3/2 for logarithmically correlated variables, as contrasted with the case of short-range correlated variables, attracted some considerable attention in recent years. So I refer to a nice recent paper by Dean Groy and Zituni, where they provide rigorous arguments in favor of existence of this universality class for Gaussian logarithmically correlated variables. And I'm going very briefly discuss what these authors claim. Before that, I just briefly compare numerics for statistics of maximum of these circular polynomials, just for small sizes, this 1 million samples of matrices of size 50, so moderate, very moderate size, but already I think agreement with analytic prediction is very reasonable. So there are reasons to believe that this is correct prediction. Now, returning back to this work by Dean Groy and Zituni, which in fact is not isolated work, but it accumulates the knowledge obtained by various sources, in particular by Brunson and Zituni and some others, on consistent work on extrema of Gaussian free field, because two-dimensional Gaussian free field is a prototype for all logarithmically correlated processes. And really, this is the point when probably the contact to random planar geometry of this talk is the most obvious, because this 2D Gaussian free field plays, as we know, a very important role in underlying, for example, the model of Liouville quantum gravity, which will be discussed in this conference and was also mentioned a few times. So, but this is only one example, although probably most generic one. So let me very briefly describe discrete logarithmically correlated Gaussian fields as they described in the work by Zituni and collaborators. So consider d-dimensional lattice and box of side lengths n with just left bottom corner located at the origin for convenience, and then suitably normalized version of logarithmically correlated discrete Gaussian fields is just a collection of Gaussian variables associated with every side of this lattice with the variance not of the lattice but of this inside this d-dimensional box, sorry, of size n. So the variance is related to the size n as 2 log n, and the covariance structure of the values of these Gaussian variables at two different sides of this lattice. It contains a logarithmic term, and it may contain, and in general contains, some continuous bounded function, at least far enough from the boundaries of this box that is bounded. So what is known, what is predicted about maxima of this collection of random Gaussian logarithmically correlated variables? So if we set Mn for the maximum, then you already should recognize this structure. It appeared on the previous view graph, but with d is the dimension of this box. So basically, you should relate in your mind d equal 1 to the example that I showed to you, but in general prediction that there will be leading term square root of d log n in the appropriate normalization, then these 3 halves divided by d log n, and then the rest will be a random variable. The difference between the maximum and this deterministic value is predicted to be given by Gumbel distribution with random shift. So basically, the probability density of this variable y is characterized by such expression, where constant c depends on detail of really this covariance on two scales, on the distances of order of n and on distances of order of unity. So it really will vary from it will vary. It will vary from one, say, model of in this class to the other, but this general shape is predicted to be universal. The problem is that this is not very explicit description of the probability density, since this expectation goes over distribution of random variable z, which is called in this context so-called derivative martingale, and given explicitly as some really related to the values of this phi, exponentiated, and also there is a prefactor. But presently there is no rigorous, and also in fact there is no heuristic way of extracting explicitly distribution of this random quantity. So what I'm going really the content of this talk, that in some models we can bypass this difficulty and give more explicit distribution, really explicitly in some sense explicitly evaluating this average, or characterizing this variable z, but not from this definition, but really bypassing this difficulty. Okay, these are results proved for Gaussian logarithmically correlated fields, but it's not immediately clear what is the relation between those objects and characteristic polynomials of random matrices. So my goal is now to show that there is some relation, and although this log of characteristic polynomial is logarithmically correlated Gaussian field asymptotically. In order to appreciate this, let us start with the simplest case. And simple case is this circular case, not the case of Gaussian unitary ensemble. Also, you've seen that the distribution for the maximum has more explicit characterization in this case. Again, this is characteristic polynomial of the corresponding random unitary matrix taken uniformly, sampled uniformly with Haar measure from the unitary group, and consider its log mod. By historical reasons, it's convenient to introduce factor -2 in front, but the important thing is just log mod. And if you take log of determinant, it will be trace of log, and then you can just simply expand in Taylor series with respect to this term. And what you get then some series, which looks in fact like a Fourier series, but and coefficients will be some traces of powers of this unitary matrix. So let us now try to understand what this structure predicts. There is a very nice result by Diakonis and Shahshahani about 20 years ago about collection, any finite collection of these traces of powers of unitary matrix. So it can be formulated in the following way. Consider a finite collection of these coefficients Vn, or a finite collection of these traces for some fixed set of indices n1 and 2 and so on, but it can be arbitrarily large but fixed. And then in the limit n to infinity, this collection of traces of powers of unitary matrix will tend to a sequence of independent, identically distributed complex Gaussian variables with zero mean and unit variance. Then it's natural to expect, and then again one can make this statement rigorous by working in appropriate functional space. It's natural to expect that basically this object in appropriate sense will converge just to a random Fourier series characterized by Gaussian coefficients Vn, which are precisely zero mean and variance 1 independent Gaussians. Then this series is an interesting object. It diverges with probability 1, but one should understand it in an appropriate functional space. So this is basically a random distribution or random generalized function. If you just formally calculate covariance structure of this Gaussian object, then it's simple exercise to satisfy yourself that it's logarithmically correlated. It's explicitly given in this case. It must be periodic because it's by construction it's 2 pi periodic, and it's given by log of mod of sign of difference t1 and t2 for t1 not equal to t2. So we see that this is a Gaussian limiting object is Gaussian object and logarithmically correlated. So you may expect some connection with this theory by Zitouni collaborators. Now, how one may approach the goal of characterizing or calculating explicitly probability density of the maximum in collection of random variables. So suppose we have a sequence of random variables, say m of them, and we'd like to find the distribution of the maximal of them. How we can approach this? So this probability density that the maximal is smaller than given value v is basically the same as expected value of the product of characteristic function for each of these variables if we introduce the notation for characteristic function theta, which is 1 if argument is positive and 0 when argument is negative. And then there is a well-known clever trick to replace this characteristic function 0, 1 function with a smooth version using parameter beta, namely using the fact that exponential of minus beta of a variable tends to 1 or 0 depending whether this combination positive or negative, if you consider limit beta to infinity. So if you are able to evaluate, so now take this regularization for each of these characteristic functions, and you end up with the following convenient formulation of the probability or representation for the probability density for the maximum. Namely, it's a limiting value when parameter b tends to infinity of the following characteristic function, really of Laplace transform of capital Z beta, where capital Z beta has the following form. It's sum of exponential of beta vi, where vi are these variables. This form resembles very much really partition functions of statistical mechanics if vi is the corresponding energy. So this is a variant of random energy model, if you wish, and this and z beta has meaning of corresponding partition function. So motivated by this type of approach, we can try to introduce a similar partition function for our random polynomial, for random function Pn of theta. Namely, natural analog is the following. It's just instead of sum, you have an integral over this interval from 0 to 2 pi, where you are looking for a maximum of your function, and then modulus of your function raised to power 2 beta, or equivalently, to make contact with this definition, is just really takes the form of a partition function of some fictitious energy, theta-dependent energy, Vn of theta, where it's precisely our function that we discussed before, just log minus 2 log mod of characteristic polynomial. In particular, if one introduces, looks at this as a problem in statistical mechanics, then it's natural to introduce the free energy, which is minus temperature. So beta plays in statistical mechanics the role of inverse temperature. So beta to infinity corresponds to the limit temperature to 0 temperature limit. So if one introduces the corresponding free energy, log of the partition function multiplied with temperature, then limiting value of this free energy is nothing else as minimum of the corresponding effective potential. And should I just wait? I'm not sure. Okay, it's just true. Okay, and in this way, it's easy to see that if we are able to evaluate this limit, we are able to get access to the global maximum of our object of interest. Now, the challenge is to find the probability density for this random object, and we proceed in the following way. So the following observation is crucial for our ability to perform this calculation. Namely, we are able to evaluate to some extent integer moments of this partition function. Partition function is given as integral, so integer moment will be given by n-fold integral of this type, where I need to perform ensemble average over this hard measure on the set of these unitary matrices of product of powers 2b of modulus of characteristic polynomials. Now, a nice feature of random matrix theory that this type of average is well known to be given by certain Topless determinant, and asymptotics of this Topless determinant for sizes for big sizes of matrix is also very well known. It was conjectured in 60s by Fisher and Hartwig, and then after that rigorously proved by Vida. And it's given basically by the following expression. So if one fixes arguments theta 1, theta 2 up to theta n, and let capital N, size of the matrix. So this small case n is our moment, but capital N is size of the matrix. If it tends to infinity, then asymptotically one gets this factor expressed in terms of Barnes function again, and then products of differences between these spectral parameters. Basically, it looks like van der Monde determinant, but raised to power minus 2 beta squared. So one then takes this value, this expression, substitutes back, and tries to say something about this integral. And crucial observation is that in this particular model, this integral can be evaluated explicitly because it's just a particular, in fact, the simplest version of the celebrated Zelberg integral. Really, this moment is given by practically by Euler gamma function of argument 1 minus n beta squared in this interval, and otherwise this integral diverges. But it's already enough to say something about the probability density of a random variable z. Important factor ze to n, it sets scales for the random variable, but fluctuations are controlled by this gamma. So for beta, in order this interval making any sense, beta should be larger than 1. Smaller than 1, of course. 1 over beta squared should be larger than 1. But we remember that our interest is in beta to infinity. So one needs to tell something about this probability density for beta eventually big, but we can extract information only for beta smaller than 1. At this point, really, some physically motivated conjectures about behavior of the corresponding probability density come into play. It's basically the picture of what is going on. I'm going to describe it in the next view graph. The overall picture was suggested. It first appeared in the work by for very specific model, basically for branching Brownian motion model in the paper by Spohn and Derrida, but then more general heuristic arguments were given in a paper by Carpentier, Ledusal, and then also supported by some explicit calculation in a related model. So I'm going to describe what is this scenario. So how can one continue, or at least to understand what's going on when beta tends to infinity. So the idea is the following. We know that the typical scale of this partition function asymptotically is given by ze, which I gave on the previous view graph, really this ze. So let us normalize our z by this typical value, and then consider precisely the object that already appeared, this basically generating function for the maximum that I already described. Then, using the moments which we were able to evaluate for beta small, namely beta smaller than 1, when they were well defined, one can restore basically this generating function from those moments, and it's explicitly given by its integral representation. And this integral representation is very convenient, but it hides a very nice fact which is not immediate to understand if you look at this integral representation. But fortunately, you can have another integral representation as integral contour integral, and then evaluating this contour integral by residues, one comes to representation of the same object in terms of really a series. And then one looking at this series, one immediately observes that this series has a very interesting property. It depends on a parameter beta, but in such a way that if you change beta to 1 over beta, it goes to itself. So we call this property high temperature self-duality. So this generating function remains invariant if you change beta to 1 over beta. Although this expression itself is only valid for beta smaller than 1. So one should, this property is nice, but it does not allow by itself continuing to beta smaller than 1, but rather one should give additional insight into this behavior, and based on several inputs, going back to rigorous work on really by Spohn and Derrida for specific model, and then by some non-rigorous heuristic physical arguments, really we believe that the following scenario takes place. Really, in the point beta equal 1, the freezing phase transition takes place, and it's conjectured that is described by the following scenario. All objects which are self-dual in the high temperature means small beta. In small beta or high temperature phase, they just freeze to the temperature independent or beta independent value precisely at the point of self-duality. Point of self-duality is beta equal 1 when obviously, and in the point beta equal 1, this integral, if you put here beta equal 1, you immediately see, okay, you may see, those of who you remember the integral representation for Macdonald function, recognize that it can be, that this gives you this Macdonald function, and then we have this this object for all beta, if we believe in validity of this scenario, and this is precisely how one arrives to this distribution of the maximum for CUE polynomial in this case. So this scenario is supported by heuristic renormalization group arguments by Carpentier and Ledoux-Salle. Okay, it's also supported by numerics, as I showed to you that consequences of this scenario can be verified, not only on the example that I showed to you, but also in some other examples. And so far, they reasonably agree with prediction of this scenario. And also recently, there were also rigorous works which confirmed some, although not all, features of this scenario, but still already there is a much better rigorous understanding of this freezing phenomenon due to two important works by Arguin and Zindi, and by Subak and Zitouni, who really gave nice rigorous insights into this freezing, into suggested freezing mechanism, although the role of self-duality is still sort of mysterious. It doesn't show explicitly in these works, but some consequences of this freezing really can be verified rigorously. Now I'm back to my original problem, really behavior of maxima of random polynomials from Gaussian unitary ensemble of Gaussian distributed Hermitian matrices. So how to make contact with Gaussian logarithmically correlated process in this model was shown in our work with Boris Horozhenko and Nick Sim some time ago. Namely, one can follow the same strategy as for circular unitary matrices, expanding log determinant, log of models of characteristic polynomial, but one should find appropriate basis. And it turns out that appropriate expansion is in terms, this time is not Fourier series, but a series in Chebyshev polynomials, which are defined here in the interval -1, 1. Let me remind you that this is precisely the interval supporting asymptotically the density of GUE eigenvalues in the normalization chosen. So one can show basically that expansion also goes in traces of these Chebyshev polynomials of the corresponding matrix, and the remainder term which exists in this case is small and can be controlled. And there is very nice analog of Diaconi-Shahshahani result for the traces of powers of unitary matrices. Here, they are traces of precisely Chebyshev polynomials. They appeared naturally in some works, in a work by Johansson, who demonstrated that again, if you fix indices, set of indices of these traces, and allow size of the matrix tend to infinity, then do I have any holes to get it back? Yeah. Okay. It always jumps forward. Okay. So corresponding set of coefficients, then finite set of coefficients tends to a collection of IID real, this time real standard Gaussian random variables. So then working in appropriate functional space, it's natural to consider again a log mod of characteristic polynomial but subtracting its mean value, so centering it, and then one can show that it converges in appropriate sense to random Chebyshev Fourier series, basically series in Chebyshev polynomials with random Gaussian coefficients. Okay, overall factor 2 divided by square root of n, and these ANs are independent Gaussian, standard real Gaussian. Then one again can evaluate covariance structure of the associated generalized Gaussian process, and it's given explicitly, just explicitly logarithmic in this case, for arguments not equal to each other. So we again see that log mod of characteristic polynomial for this ensemble is related to a different instance of logarithmically correlated Gaussian field. So now we are going to proceed along the same steps as before for CUE, but we will see that there are some subtleties and really new ingredients, at least technically. So we do precisely the same. So we have this object. We'd like to find maximum of this object in the interval -1, 1, support of eigenvalues, and then we introduce the corresponding partition function. What is the difference with previous case? In the previous case, density of eigenvalues of random matrices along the circle was uniform. It was 1/2 pi. So corresponding partition function was just integral of exponential minus beta log mod. Here it turns out that appropriate set or appropriate family of partition functions to be considered should include a factor rho of x to q power integer, to arbitrary power q, positive power q, where rho is nothing else as asymptotic semicircular density of eigenvalues of the corresponding GUE matrix. Parameter q at the moment is just arbitrary non-negative parameter. Naively, if you just do naively a comparison with previous case, there is temptation to put q equal to 0 and just have only this term. And also, naively, you may expect that since we are interested effectively in beta tending to infinity, this term, which is beta independent, this q is beta independent, should not, to the leading order, play any role. But it turns out that this is, in essence, a wrong statement. And really, in order to implement this freezing philosophy and extract the probability of maximum, one needs to keep this factor, and only for particular some values of q will be singled out and will help to continue to beta to infinity. So so our next goal is to perform the same calculation as before and to evaluate integer moments of this partition function. So you just consider product of k integrals of this sort, and you need to evaluate the product of modulus of corresponding polynomial to power 2 beta as before. This time they are given not by Toeplitz determinants, but by Hankel determinants. But fortunately, a few years ago, there was a beautiful work by Igor Krasovsky, who I hope will be here today, but he's obviously, because he's on second program at the moment, but he is away. But anyway, he provided very nice and precise characterization of these objects, of this asymptotic behavior of these Toeplitz determinants. And now they're given by a more complicated formula as in case of CUE, but still this Vandermonde to some power structure remains. And in fact, if you consider this as a generating function in some sense for random characteristic polynomials, you see that it can be exponentiating this term. You see that basically it looks like there is Gaussian correlated process at the background, but also there are other terms, and eventually it turns out they play the role in when you'd like to extract explicitly the distribution of the maximum. But anyway, we can extract, by the way, asymptotic, which is important for our calculation, asymptotic behavior of the mean value of log of modulus of characteristic polynomial, and then we substitute this expression back, and after some manipulation, it turns out, fortunately, the corresponding integrals moments are again given by version of the Zelberg integral, but this time the full version. So if any of you know how general version of Zelberg integral looks like, it's a product of ratios of nasty gamma functions. So now you should be able, or should attempt to continue from these nasty moments, seemingly defined only for integer k, if you look at them, at least for the face value, how to continue it and how to extract the generating function of this sort. But these are unpleasant but technical issues which could be done. We know some methods of really building this type of generating function from those integer moments. We also extract typical scale of the partition function from this calculation from the moments, and we proceed in the same way. And what is now a second contact to really two-dimensional thing, to the two-dimensional gravity maybe. Really, it turns out that in order to perform, really to represent this distribution of this random variable for the maximum from integer moments, the only way is to use nice function, which is also sometimes called a generalized Barnes function, but which most explicitly we found in the work by Zamolodchikov brothers on Liouville field theory. So this is an object they use to represent some conformal factors arising in that theory, and this function, which log of this function has explicit integral representation, it possesses very nice properties. It's self-dual. When you change parameter beta to 1 over beta, it goes to itself, and also nice shift properties. And combining all these properties, we can investigate whether our object, our generating function for the maximum, is self-dual or not. And it turns out that in the whole family of Q-dependent generating functions, there is only one particular value for Q equal 1. So when you just weight everything with just density of eigenvalues in the first power, which satisfies self-duality relation. Then we rely again on that principle that I mentioned to you, that thermodynamic properties which in a high temperature or low beta phase are self-dual function of the inverse temperature beta retain for all beta larger than 1 the value they acquired at the point of self-duality. This fixes uniquely this G beta for beta larger than 1 and gives that double-sided Laplace transform formula that I started with as our main result for the explicit characterization for the maxima of GUE polynomials. So let me summarize. So I hope I gave to you a flavor of the fact that log mods of characteristic polynomials of random matrices, in particular I discussed CUE and GUE, but one can give, I mean, it should be, I think, statement valid in general. They are examples of the regularized version of log correlated and asymptotically Gaussian processes, generalized processes, random distributions. But they are, in this sense, they are close relatives of 2D Gaussian free field. But they are one-dimensional instead of two-dimensional relatives. So they share many properties of that interesting object. And exploiting the methods of basically statistical mechanics, we computed explicitly, or attempted to compute explicitly, the distribution of maxima of these characteristic polynomials over the intervals of eigenvalue support. Our calculation is based on the conjectured nature of the freezing phenomena, which in fact in other incarnation appear in spin glass literature, and it's very closely related with freezing phenomena in spin glasses. Basically, it's just incarnation of that. One even can give meaning of this freezing phenomena in the language of spin glasses as one-step replica symmetry breaking. And this also gives some insights into mechanism of this freezing. Although it's not rigorous, but it's very informative. And important role is played by high temperature duality. Without that duality, we do not know how to continue from high temperature phase to zero temperature, thereby extracting maxima. And final note that in fact the underlying motivation for this project was the following. One can show that in the same sense, log mod of a Riemann zeta function sufficiently high up the critical line where all non-trivial zeros belong to according to the Riemann hypothesis is yet another example of effectively log correlated Gaussian process. This idea we formulated with John Keating a few years ago, and now there is ongoing work by Paul Bourgade and by other just along these lines. And the above picture can be further translated into making non-trivial conjectures about statistics of moments and high values of Riemann zeta function along the critical lines in some finite intervals. And this is a problem of long-standing interest in mathematics, and we believe our approach and results provide new interest and light on these problems. Thank you.
Are there any questions?
Yes, so I find it quite remarkable that you have these explicit calculations of the fluctuations around the maximum. So you also showed that the values of the polynomial approximately behave like a log correlated Gaussian field.
Exactly.
Can you get the law of the fluctuations directly from the covariance kernel?
No, interesting case. In CUE case, yes, you can just naively replace it with its limit and you get it. In GUE case, no. It turns out that some factors which are not simply covariance, but they are, okay, I don't know really the nature of them, but this formula due to Krasovsky, maybe I come back to it. This formula, okay, if I just naively use this Gaussian approximation, it will be only this term. But there is also this type of terms. And it turns out that indeed one can check that distribution will be different. It will be not drastically different, but explicitly it will be different formula. So it seems that Gaussian nature is there and it plays very important role, but nevertheless, not in all examples, it's just enough. Really, these objects are only asymptotically Gaussian, and it seems that these fluctuations of order of unity know about that. This is a message.
Other question? Yes.
So I guess the self-duality is a bit like the duality between SLE kappa and SLE 16 over kappa.
No, morally, yes.
And
It's very close to it.
but so for instance, so is there some similar phenomenon already? I don't know, in branching Brownian motion.
Okay, in branching Brownian motion, everything what I said, okay, almost everything can be really rigorously proved. there is self-duality. It's not mentioned by this name, but it's explicit in traveling wave approach to for example, employed by Bremson or by Derrida-Spon in this context. So it's explicitly there. No doubt that it's there. Beyond that case, it's still challenge to see it.
Let's thank Jan again.